So this is section 12.1. It's the only section that's done in chapter 12 for Stat 50, and it is coming from chapter 12 called Analysis of Variance. So section 12.1 is one-way ANOVA, and ANOVA is just an acronym for Analysis of Variance. So that's why it's called ANOVA. And the big idea behind ANOVA is simply that it's going to take a look at 3 or more population means, and it's going to see how similar they are, or if at least one of them is different. So back in chapter 9, section 9.2, we looked at comparing 2 population means. But what if you had 3 population means? So what if you had 3 samples and you wanted to compare them? Well, you could do a hypothesis test on the first 2, and then you could do a hypothesis test on the second and the third, and then you could do a hypothesis test on the first and the third, and you could do a bunch of different hypothesis tests, because you'd have to do, because each hypothesis test from section 9.2 is only 2 means. So if you have 3 or more, then there is just 1 test you can do, and that is called ANOVA. So there is data that you're going to have that is categorized with 1 factor or treatment. So there's similarities between the data, but every one of them has a different treatment. So hopefully you watched the video that I linked to before linking to these videos, because that would be a video I would show in class, and it is very helpful for just getting the idea of ANOVA. So the hypotheses for the ANOVA test are quite straightforward. It's just that either all of the means are equal or not all of them are equal. So that might mean one is very dissimilar to another, or it could mean that all of them are dissimilar to each other. But all you know from your alternative is to see if at least one of them is different, not all of them are equal. So what we're going to be doing is we'll look at sample means from a population, and if they're all close, well, then we can't say that they're different. So in that case, we're going to fail to reject our null. Now, if these sample means are very far apart, then what our ANOVA test will most likely tell us is that we're going to have to reject the null, the idea that all of the population means are equal. So there is a hypothesis test for this, last hypothesis test. We want to have the populations coming from a normal distribution. The population should have the same variance, which is your standard deviation squared, and you want independent simple random samples. So we'll talk about that as we look at examples. Level of significance, still alpha. The hypotheses look like this. Either your H naught is that all the means are equal, or at least one of the means is different from the other. Similar to a chi-squared test, this is always going to be a right-tailed test. We are going to be using a new distribution. You will not see a table for this distribution because we just use the p-value method and we don't use a table. If you did use a table, there's like 10 tables or something for this distribution, so we do not do that. Things to kind of think about but not spend too much time on are like going deep into ANOVA, which we don't do in this class, but you could. But you're thinking about when it comes to degrees of freedom, it has to do with how many values you have in your samples, as well as like how many categories, how many means you're comparing, things like that. So don't worry too much about this right now. I'll talk a little bit more later. So the test statistic is coming from something called the F distribution, and that's what you see here. This is the F distribution. So notice it's sitting to the right of like an axis, and that is saying that, similar to the chi-squared, it's always going to be positive. But notice it's not quite as sharp as the chi-squared distribution. So of course this is something that some statistician discovered a long time ago. And where this number is coming from, I mean, your calculator will just pop it out for you, but the big idea behind ANOVA is that when you have 3 sets of data, it looks at how much variance, so a measure of how much the data values vary from one sample to another, but also how much each sample varies within itself. And then it's the ratio of those 2 things that gives you your test statistic. There is a calculator function. There is a FCDF for this. That's, of course, adding up just like normal CDF or TCDF, the area. So that is an option, but it's not a focus that we have. We use, we'll just be focusing on the calculator. So same thing, we want a small p-value, we want it to be less than alpha. And then we reject or fail to reject based on our decision, and that's it. So let's take a look at an example. So we have 3 groups, randomly selected students, and they were given a dosage of statistioprazole, a new drug that supposedly increases a student's ability to perform statistics. How nice would that be? So each group was given a statistics pretest, and then 2 groups were given some statistioprazole. So one group got 10 milligrams and one group got 20 milligrams. Again, this is just kind of a not true thing. There is no statistioprazole, I'm sorry. And then one group got a placebo. So we have 3 groups. And then afterwards, all groups took a post-test. And we want to see if we have the mean test scores from these 3 groups. How close are they to each other? Or is at least one of them very different? So we're going to do that with an alpha of 0.05. So, your null is just that the means are equal. If you want to be a little more showing that you understand, you might say that the mean of the students that got the placebo is equal to the mean of the students that got 10 milligrams is equal to the mean of the students that got 20 milligrams, for example. That would show the 3 means that you personally are dealing with in this problem. And then your alternative would just be at least one of the mean test scores is different than the others. So notice that the only kind of thing I'm adding from what we saw in the notes is test scores. So because that's what we're talking about here is mean test scores. Okay, so here is the whole thing. And again, our focus will be on the calculator, but for some people who are interested, I want to show them a little bit about how this works for ANOVA. So we have our 3 groups, one placebo group, these people got 10 milligrams, these people got 20 milligrams. We're sticking with smaller, a very small sample size here just to make it easier, but you'll notice that all of our n's are 4. And what we can do is you can take a moment if you want, and you could find the mean and the standard deviation for each of those 3 groups. So you could put one in each of your 3 lists. 3 lists, that would actually be a good idea because we'll do it in the calculator. So put all of them in a list. So pause, put them in a list, see if you can find the mean and standard deviation, write it down, and then come back. Okay, so here are our means, and I put the standard deviation, but notice I square it because this is actually variance here. This is the variance of all of them, and that's important to understand because this is analysis of variance. So those are all your standard deviation squareds. So I have the squareds on it. Notice that we can see pretty quickly that the group that took 20 milligrams of statistioprazole got an average of a 9, got a mean of 9 on their post-test, whereas the placebo group had a mean of 5.5. So there's definitely a difference there. The 10 milligram group, 7.25, that's in the middle. But the idea is just to think about our test is determining how far apart those values are. So the variance between the samples comes from your n times, this is the variance of the sample means. Variance of the sample means. So 4 is our sample size, and then in here, this number here is the variance of the sample mean. So if you put, basically if you put 5.5, 7.25, and 9 into a list, and found the variance of it, well, technically you'd find the standard deviation and then we'll square it to get the variance, you should get 1.75. So the standard deviation of these three values, the means, gives you 1.75, we square for the variance. So that's how much variance there are between samples. So from placebo to 10 milligram to 20 milligram. The variance within the samples themselves comes from the mean of the sample variances. Mean of the sample variances. So this one's a little easier to do out. So it's taking those three variances, 2.08 squared, 1.5 squared, and 0.8165 squared, and then finding the mean of those. So dividing by 3. Okay. Then we see what we get. And we should get over here, sorry, I should have done this out. This is going to give us 12.25. This is going to give us 414. And then this is the key to see. The key thing to see is this test statistic, you can call it F star if you want, is that value, the 12.25 divided by 2.414. That's actually what your test statistic is. Now, it's not going to be often that I would ever ask you to find the test statistic because you can see how much work it is. It's a whole lot of work. And so, especially depending on what your sample sizes are. So if we do this, we get about 5.07. So that is a measure of, that's your test statistic. It's a measure of strength. But our focus will be on the p-value. So if you have your three placebo group, 10 milligrams, 20 milligrams in three different lists, what you want to do is you want to use the ANOVA test to get the p-value. So what you can do is you can go stat over to tests. It is the bottom one, so it's best to scroll up. That gives you, just as ANOVA. And now what you would need to do is choose your three lists, separate them by commas. So if it's list 1, comma, list 2, comma, list 3, close it up and then press enter. It's going to give you the test statistic that we already found, and it's going to give you the p-value, and that's really all you need. Now you should also see the two numbers that we found here and here. Your calculator will do those as well, so you should see those. So what we'll do now is find our p-value. So the p-value that you should see in the calculator, it's pretty small, 0.3354. Our alpha that was given to us with for part of the problem is 0.05. And we can see that our p-value is less. So what's happening is we have some test statistic, 5.07, that's a test statistic, and the p-value is 0.3354, and we compare it to our alpha. So it's really just seeing there's, how far out there is our data compared to what would be normal if the null is true. And now we just write our conclusion. So the p is low, so the no must go. So we're going to reject H naught. You can see down at the bottom of the screen here, you've got how you do this in the graphing calculator. Now, the conclusion is, just like always, there is sufficient sample evidence to, and then we can come back, think about the claim. The claim is that the mean test scores are the same. So our claim here is the null, that they're equal. So when we come back and we write our sentence, and this is very common for the chapter 11 and chapter 12 sections, we are going to have to say that we have sufficient sample evidence to warrant rejection of the claim that the mean test scores are the same for each treatment. And so this really tells us, hopefully you see, that taking the 20 milligrams of statistioprezole compared to the 10 milligrams compared to a placebo will give fairly different test scores. And that is a way to basically measure whether something might be effective. Now what we could do is we could do a hypothesis test, say from the placebo to the 20 milligram group and the 10 milligram group to the 20 milligram group. Now we could do other hypothesis tests to see how far apart, like what kind of evidence we have in support of two of them. But this would be a great way to start off, because if you fail to reject this, well, then there's nothing else you would need to do because they're too similar. But if you reject, maybe you'd want to go further than that and see which of the means are actually the farthest apart from each other.